So we're going to continue our conversation about discrete probability in video 3 by looking at conditional probabilities. So here's the basic idea. We might be interested in the probability that an event E occurs, but another event F may already have occurred, and this event F may impact or affect the probability that event E occurs. So what we want to identify is, because F has occurred, has that changed the probability of E? So for example, an event F that may have already occurred is I've rolled the first die. And recall, this is the table that we looked at earlier where we had two dice being rolled, die 1 and die 2. And then we had 6 outcomes that could happen on each die, and then we took the sum of the two rolls, and then those sums became our sample space. So our sample space was the sum of two rolls of a dice, 6-sided dice. And the size of that sample space, we had 6 possibilities times 6 possibilities, giving us 36 possible sums. And then we could have an event, F, that's already happened, and that event could be we've already rolled the first die and we know the result of that roll. And then what we could ask ourselves is, does that result impact the probability of other events occurring? So F could be a 6 was rolled. On die 1. So we rolled a 6. Okay, so if a 6 is rolled, you can see there's only 1, 2, 3, 4, 5, 6 possible sums that you can construct with that 6 having been rolled. And we may be interested in some other events. We may be interested in event 1, that the sum of the two rolls is a 5, for example. We could be interested in an event 2, that the sum is a 7. We could be interested in another event, event 3, that the sum of the two dice is a 9. Those are all things that we could be interested in. And the probabilities of these things may or may not be impacted by the fact that a 6 was already rolled. So the probability that the sum is a 5, typically, if we don't know that a 6 has been rolled already, usually the probability that we get a 5, or the probability of event 1, is 1, 2, 3, 4 in 36, because 4 of the sums out of the 36 sums is a 5. Usually the probability of a 7, getting a 7, is going to be, we get 1, 2, 3, 4, 5, 6 ways to get a 7 when we add 2 die. And that's going to be out of the 36. And usually the probability that we get a 9 for our sum is going to be 1, 2, 3, 4, a 4 in 36 chance. But if we know that F has been rolled, that's going to change the game. Sorry, if we know that 6 has been rolled, if event F has happened, we've rolled a 6, that changes the game. So for example, the probability of 5, if F has occurred, well, if we've rolled a 6, there's no way to get a sum of 5. We are already past 5, and the only possible sums are 7 through 12. So there's going to be a 0 out of, hey, F has happened, we rolled a 6. There's only 1, 2, 3, 4, 5, 6 things in the sample space get a 6 on the first roll, and 0 of them are 5s. So there's no shot at getting a 5. Whereas the probability that you get a sum of 7 is going to be, hey, there's 1 7 in that set of 6 outcomes that are possible if a 6 has been rolled. So you're going to have a 1 in 6 chance, which is actually the same probability that you had before, because 6 over 36 would reduce down to a 1 in 6 chance. So the fact that I rolled a 6 first had no impact on my chances of getting a 7, whereas rolling a 6 first reduced my chances from 4 in 36 to 0 in 6, and the probability that I get a 9 for my sum, well, 9's in there. It's one of the things that you can get if you roll a 6 first. And there's only 6 things that can happen. There's a 1 in 6 chance that I get a 9. And if we scale this up by multiplying by 6 over 6, so we get 6 in 36, we can see that we have a better shot now than we did before. Originally there was only a 4 in 36 chance that we get a sum of 9. But once we know that a 6 has been rolled, now I have a 6 in 36 chance, or 1 in 6 chance of getting a 9. So the idea here is there can be events that we're interested in, and our knowledge of an event having already occurred could impact the probability that the event we're interested in happens. Just like it did here, we went from a 4 in 36 to 0 in 6 shot of getting a sum of 5, whereas so we went from having a chance to having no chance. We had a case where there was absolutely no impact on our chances, and one where our chances are now improved. So this is the basic idea behind conditional probability. What we want to do next is put a formula to it so that we can have a formulaic approach for calculating these probabilities. And so here's the basic idea. So we're going to do the probability of E given that F has happened. So this notation here, this is, I'm interested in the probability that E happens. The vertical bar, read it as given that some other event F has already happened. So here's the idea. The idea is once F has happened, you are working out of a new sample space, right? You don't have 36 things that can happen anymore. You only have, if 6 has happened, you only have 1, 2, 3, 4, 5, 6 things that can happen. So to calculate the probability of E, given that F has happened, the size of F becomes the denominator. It is the new sample space. And what we need to know is how many of E occur in the sample space generated by F. So the idea is that the number of items in our event E that occur in that new sample space is just going to be the intersection between the event E and the new sample space F. In other words, when we wanted a 7, the only 7 that we could get was in the intersection of the sum is 7 and a 6 was rolled first. The 7s outside of that intersection, those are all 7s that are not possible to get. So we need to know the size of the intersection of the two events. We need to know what is the size of this intersection right here. How many of the thing that I want are actually in the thing that has occurred. So we need to know the size of that intersection. And we can multiply this by an interesting form of 1. We can say, hey, E and F both came from an original sample space S. And S, because it's finite and countable, because that's what we've been working with, is finite countable sample spaces, he has some size. And so I could multiply by 1 over the size of S divided by 1 over the size of S. And this would just equal 1. 1 over the size of S divided by 1 over the size of S is just a 1. So this times 1 is still this. It will look different but be equivalent. So when I multiply the size of E intersect F times the size of 1 over the size of F, I get the size of the intersection over the size of the original sample space divided by, now I'll take the product of these two numbers, we get the size of F over the size of the original sample space. And if we look at this, we can see that the size of S divided by the size of S would give us 1, would give us back the original ratio. They're both in the denominator position, so they'll give us a 1 under division. And then if we look carefully at this, the size of the intersection divided by the size of the original sample space is just the probability that the intersection occurs based on the definition of probability. And the size of F divided by the size of the original sample space is just the probability that F happens. And so that generates these two equivalent ways, two different but equivalent ways of calculating the probability of E given that f has already occurred. So let's look at this in practice. So here's an example. Given the non-negative integers less than 20, non-negative integers less than 20, what is the probability that you randomly draw a 4 given that you drew a multiple of 4? So the sample space in this case is going to be the non-negative integers less than 20. So this is the set of positive integers from 1 to 19, which means that the size of that sample space is just 19 items. We're interested in the event that we draw a 4 from that sample space. So we're interested in the event draw a 4, and that just looks like this. There's only one 4 in that sample space. And we have another event that we drew a multiple of 4. Draw a multiple of 4. And we're told that we know this event has happened. Draw a multiple of 4. So f, he looks like this. He has all the multiples of 4 less than 20. The positive multiples of 4 less than 20. So he has 4, 8, 12, and 16. And that means that the size of f is just equal to 4. And then we need to know about the intersection. So right, we're interested here in the intersection between E and F. So if we look at the intersection, E intersect F, well, what's he look like? Well, the intersection between E, which contains 4, and F, which contains the multiples of 4, is just 4. 4 is the thing that is common to the intersection. And we see that the size E intersect F, that size is just 1. And now I believe we have all the pieces that we need. So we can say, hey, I want to calculate the probability of E happening, the probability that I draw 4, given that F has already happened. In other words, I've drawn a multiple of 4. And if I use this form of the formula, I see that I need to put the probability of E intersect F divided by the probability of F. Well, the probability of the intersection is just the size of the intersection divided by the size of the sample space, which is 19, divided by the probability of F is just the size of F, which is 4, divided by the size of the sample space, which is 19. And again, we see that the 19 divided by 19 is 1, so we wind up with 1 over 4, a 1 in 4 chance, which we could have gotten directly by using this version of the formula. We could have gotten it directly. We could have said the probability of E given F is just the size of the intersection of E and F divided by the size of F. And we know the size of the intersection is 1, and the size of F is 4. And here's really the sizes showing up here, and the size of the sample space canceling. So even though we could have used this form, I like using this form because it shows the size of the sample space canceling out, and you aren't always able to identify the sizes of the sample spaces. Sometimes what you have is the probabilities only. So understanding that you can just take the ratio of the probabilities is a powerful tool. So here's another example. What is the probability that a bit string of length 4, so a sequence of 4 zeros and ones, the bit string, a sequence of zeros and ones, what is the probability that a bit string of length 4 generated at random so that each bit is equally likely, so there's no weighting to any of the bits. We want to know what is the probability that it contains 2 consecutive zeros given, there's my given that the first bit is a 0. So my sample space, if we identify the sample space is bit strings length 4. So they are going to look like this, and they're going to have either a 0 or a 1 in each position. So we know that there are two choices for each position. So by rule of product, we multiply two choices times two choices times two choices times two choices. So we see that the size of the sample space is just 2 to the 4th, or 16. The event that we're interested in, the event E, in which we are interested, is to the event that we get two consecutive zeros. We're interested in two consecutive zeros. The event F that has already happened is that we have a 0 in the first bit, right? The first bit is 0. So this event that's already happened is a 0 in the first bit. So if that happens, if a 0's happened here, then there's only one thing that can happen, but there's still two choices for each of the other 3 bits. So the size of F turns out to be 1 times 2 cubed, which is just 8. And now we need to know something about the intersection between E and F. So the intersection between E and F, this is just going to be that the first bit is 0, that's from F, and there are two consecutive zeros. So we can kind of systematically walk through and try to look at this intersection. What does this intersection look like? Well, we're told that the first bit must be a 0. So one way to get two consecutive zeros, if the first bit is a 0, is to have a 0, 0, 1, 1. Another way to get two consecutive zeros, if the first bit is a 0, is to have a 0, 0, 0, 1. Another way to do it is to have a 0, 0, 0. Let's see. Try to be systematic. We could have a 0, 0. We could have a 1 in this position and a 0 here. That would be another way to do it. Another way to do it would be 0, 0, 0, 0. That has at least two consecutive zeros. It's an at least, not exactly. And then the other way that it can happen is you could have a 0, but instead of having a 0 in the second position, these are all the ways that we can do it where there's a 0 in the second position, all possible combinations. And then we say, hey, the other way it can happen is there's a 1 here. But if there's a 1 here, then to get two consecutive zeros, you have to have two zeros there. So when I look at this, I see that there are 5 ways to have a 0 in position 1 and two consecutive zeros. So the size is going to be 5, and then we can work out the probability. The probability of E, given that F has happened, is just going to be the probability of the intersection, right? The probability of the intersection divided by the probability of F. So the intersection has 5 elements in it. The original sample space had 16 elements in it, divided by F had 8 elements in it, divided by the sample space had 16. Those 16s are going to give us a 1 after we do our division, so we're going to wind up with a 5 out of 8 chance. And that makes sense. There's 5 things that have two consecutive zeros out of the 8 possible things that you can create that begin with a 0. So last example. What is the conditional probability that a family with 2 children has 2 boys, given, there's our given, that they have at least 1 boy? So the sample space here is to have 2 children. And the size of that sample space, if you're having 2 children, you have choice here. It could be a boy, girl, or boy, girl. So there's 2 choices for the first child, 2 choices for the second child. So there's going to be 2 times 2 is 4 possible permutations. Order does matter. If you have a boy and a girl, that's different than having a girl first and then a boy. At least it matters to the kid. So order matters. So the size of the sample space is 4. And we're interested in having 2 boys, the event that we have 2 boys. So the event that we're interested in is have 2 boys. That's the event we're interested in. And there's only one way that that can happen, right? To have 2 boys, you'd have boy, boy, right? This event is the first kid is a boy, the second kid is a boy. That's what that event looks like. And then we have another event that we have at least 1 boy. So F is at, we know they have at least 1 boy. So having at least 1 boy, what does that look like? Well, that's, you can have boy, boy, boy. You could have, whoops, we're doing 2 kids, not 3. You could have boy, 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 girl, girl, boy. Those are the only 3 ways to have at least 1, right? The only other option is girl, girl. So the size of F is equal to 3. And then we need to look at E intersect F. And this is, hey, the intersection between having 2 boys and having 1 boy, but this intersection is just boy, boy. So the size of that intersection is just 1. And so then we can say, hey, the probability that we have 2 boys given we have at least 1 boy is going to be equal to the probability of the intersection divided by the probability of F itself. And the probability of the intersection, there's 1 element in the intersection, that's the boy, boy, over the sample space, which is 4. Size of the sample space is 4, divided by the probability of F is the size of F, which is 3. There are 3 possibilities in F, divided by the size of the sample space. And once again, those will give us a 1. 4 divided by 4 is 1, and we'll be left with a 1 in 3 shot of having 2 boys, given that we know one of the 2 children is already a boy.